Okay, continue our discussion about the driver for unipolar stepper motor, specifically permanent magnet stepper motor. Okay, so we are talking about that specific kind of motor that are the most employed, okay, stepper motors types. Okay, L over R, or sometimes you can also find in literature constant voltage driver for unipolar stepper motor, basically are made by these circuits you can see in this whiteboard. Okay, for each of the phase you have to drive. Okay, we have a switch. This switch is called the low side switch because, say, the source is connected directly to the reference node. Then you have a power supply V, and then you have the phase you want to drive, which is modeled by the series of LA and RA, which is respectively the inductance of the, say, the winding and the resistive losses of the coil. Okay, IA is the current flowing through the phase. We talked about the turn on. Okay, and here you can see a sketch of the current flowing to the phase at the turn on when I want to energize the phase. And you see that there is not so fast action at turn on because the speed of the turn on is limited by the amplitude of the voltage V, the supply you supply to your circuit, which is, let's say, constrained by the fact that V over RA, so the on current flowing in these circuits, cannot be higher than, say, maximum allowable levels, which is specified by the manufacturers in the datasheet. Okay, what happens during turn off? During turn off, you have the interruption of the current because the switch is commanded to be an open circuit, so the current suddenly should goes to zero. This is not possible. Okay, the inductance in the winding of the phase, as say, stored magnetic energy, okay, due to the previous phase in which the current is flowing the phase. So there is such energy in the magnetic field of the inductor, and it is not possible to, let's say, make this energy to be null instantaneously. Okay, so this leads to the fact that the current IA, even after you command the switch to be off, okay, the current continues to flow. And in this case, the switch is off, but the body diode, which is, say, in parallel, is something which comes for free in the construction of the MOSFET, okay, goes into the breakdown region. Okay, so there is a small fraction of the period at the turn off in which the circuit is, let's say, operating into the breakdown region of the power MOSFET you are employing, or if you use IGBTs, in the breakdown region of the IGBT. Okay, MOSFET is off, but the voltage is, let's say, the maximum possible voltage. So let me just sketch this situation that happens during turn off. You have something that can be modeled in this way. You have the voltage V that you have here supplying the circuit. You have the phase LA RA here, and then we see that in between the drain and the source, here you have a battery, which is the battery that models the breakdown region of the MOSFET. So we can call it breakdown voltage between the drain and the source. And this S means that the gate is shorted to ground, so to the source, which is exactly the situation that you have when the MOSFET is off. Okay, so this is the nomenclature you can find in the datasheet for, say, illustrating the breakdown voltage region of the MOSFET. Okay, so this is the situation you can have at the turn off. Okay, so the current IA continue to flow, but the MOSFET is in the breakdown region. So you can now, for that circuit, you can just have at the turn on, again, write down a, let's say, linear differential equation. Okay, now the voltage that is applying to the phase is no more V as in the turn off happens, but is V minus BVDSS. Okay, it's the series of these two battery here and here that is supplied to the phase here. Okay, so you can write down the same exact equation. Remember that when you have a circuit in which you have just one time constant, then you can easily find out which is the solution of this differential equation by taking into account this equation, I infinite minus I0 plus E minus T over the tau. Tau is the time constant. Again, the time constant is always LA over RA, so the same time constant you have at the turn on is that which is valid at the turn off. But now all the terms here are different from our previous analysis, okay? Because I infinite is the current flowing in that circuit in steady state condition. So when all the transient vanished out, so the voltage, the current here is no more V over RA, will be V minus BV DSS over RA, okay? Because now we have this voltage here that previously was not present. I0 plus is the current flowing at the time instant later, okay, successive to the turn off action, okay? So this is the same over the current flowing an instant time before turning off your MOSFET, and so this is V over RA. Using this description, it can be, and replacing, say, let me just do this simple computation. I T is I infinite V minus breakdown voltage between the drain and the source of the MOSFET over RA minus V minus B V DSS over RA minus V over RA, and this is E T minus tau, okay? Some simple manipulation. You can find that this is the same as V over RA plus, okay, is not so important to write in this way, but is another alternative way. Okay, so pay attention that now the time axis has the zero at the time instant at which I have the turn off. Okay, so my expression is something like this. This is the on current V over RA, then turn off, turn on. Somewhere you have the time instant at which you command the switch to be off, so here. And so from this time instant, I have this expression, okay? So you have something that at the end will reach V minus BV DSS over RA. This is I infinite. Something like this, okay? Pay attention that I infinite here, which is V minus BVDSS, this term here is negative, okay? Because the breakdown voltage sorry, this is in this way is positive, okay? The breakdown voltage is always larger, okay? So if I take this condition, this quantity will become negative, okay? So here you have this quantity. Of course, when the current goes negative here, so in that specific say region, this evolution, the situation is not describing something physical, okay? It's just a mathematical abstraction you can have. Of course, when the current goes to zero, the MOSFET, say, reaches its steady state condition, so the fully open situation, okay? It becomes a real open circuit, okay? So here, the MOSFET has a behavior which is, say, the real situation is this one, okay? So in real circuits, and this is the mathematical, if you want, abstraction, okay? The current cannot go negative. The current, when reaches zero, becomes, say, null. The MOSFET will be open. Sorry, I have here something which is not correct. I'm just looking at the slide, okay, at the graph here. I have to say that, of course, the voltage V is, let's say, higher than the breakdown voltage, okay? Because this is the situation I have to consider, okay? So this infinite, no, it's correct, okay? No, this is negative, okay? Because this is exactly what happens. The breakdown voltage should be larger, okay? Sorry. If you choose a MOSFET with a breakdown voltage which is less than the voltage V, of course, this MOSFET is destroying, okay? So the breakdown voltage should be larger than the voltage V you have to apply to the external side, sorry. So this is correct, this is negative, okay, and that is the situation. If you want to, say, plot at the same, say, simultaneously the voltage VDS you have at the MOSFET drain to source port, then you can have that when the MOSFET is on, so here, the voltage is basically is, say, very close to zero. It's not zero. We can say that is R on multiplied the current IT, okay? So it's the voltage V on. But basically, since R on, so the resistance that you can have between the drain and the source in the MOSFET, which is conducted, can be, say, chosen to be very small. This quantity is, say, very close to zero. So it's almost a closed switch. Then here it happens that the voltage goes very high. So the voltage here is the breakdown voltage. Then what happens here when the MOSFET reaches the current, if the MOSFET is null, then the voltage becomes to be V, okay, which is less than the breakdown voltage, okay? Because now the MOSFET is fully open, okay? So when the MOSFET is fully open, the voltage across the open MOSFET is exactly the voltage supplying the circuit, okay? So here is the critical situation, if you want, in this interval. Because simultaneously we have a current which is not null, and then, say, it reaches null, but, say, in this time interval is not null, and you have a very large power because the voltage is very large. Okay, so the product between the voltage VDS and the current flowing to the MOSFET, the current IA, okay, is very large. So this is a problem. Okay, typically you are not allowed to operate the MOSFET in the breakdown voltage region. Okay, the breakdown voltage is something that is not an operating point. Okay, you are allowed, and specification datasheet always mention this fact that you are allowed to, let's say, operate with a voltage when the MOSFET is off, which is a little bit lower than the breakdown voltage, okay? But say we can say that there exists some, say, construction manufacturing techniques that makes possible to operate the MOSFET exactly at the breakdown voltage. For example, if your breakdown voltage is 600 volts, okay, typically you are not allowed to reaches when the MOSFET is off 600 volt across the drain to source part of the MOSFET, okay? But in some situations there are that are called avalanche, let's say, capability MOSFET that has this feature. In that specific situation, you are allowed to reach, let's say, the maximum possible breakdown voltage. 600 volt is possible to operate in that situation, but this capability, this avalanche capability, depends on the energy which is involved in this operation region. You are allowed to reach the breakdown voltage when the MOSFET is off, but you have to operate in this region with a minimum amount of energy which is involved. This is always related to the fact that operating the MOSFET or even the diode, whatever semiconductor power device you can have in the exactly at the breakdown voltage, increases, say, the let's say the current flow into the MOSFET. Okay, so there is an phenomenon which is a typical thermal phenomenon. Okay, it increases up the temperature of your devices. So the time, the thermal time constant typically is not so fast. So before reaching the maximum temperature, which is permissible for a semiconductor, 150 degrees, for example, it takes some amount of time. Okay, so if you are able to operate the semiconductor device in the breakdown region, but with a very small amount of energy involved in that specific situation, that the temperature has not the time to reach the maximum possible level. And so this is not inducing any permanent failures. Okay, so what does it mean? Is that I can operate power MOSFET in the breakdown region exactly at this voltage here, but you have to, say, minimize the time interval at which I operate in this time interval, okay? Because the energy will be involved will be very, very small. In the datasheet, there is a parameter which is the avalanche energy. Okay, sometimes it's called EA, okay, which is a parameter provided by manufacturers that exactly state these, say, this fact. Okay, this is the amount of energy that you can afford when you operate the device in the breakdown region before reaching permanent failures. Okay, so when you operate your MOSFET in the breakdown region, exactly at this voltage here, which is the maximum allowable when the MOSFET is off, and you are able to minimize the time interval at which you apply this operating region, minimizing the energy, then the situation is reversible. So you can go, say, you can continue to operate the MOSFET safely without any problems. Okay, but if it's not, say, accurately followed, okay, or accurately say, employed, you overcome this avalanche energy, then you can get permanent failures. Okay, so this is what happens here. So it just for, say, just an example, try to find out for that specific situation which is the energy which is involved, because understanding which is the energy involved in this specific operating region here, when the MOSFET goes into the breakdown region, maybe we have some tools to by which we can reduce this energy, okay, to make the situation safely. So let's start by computing which is the energy involved in this turn-off situation. In order to do that, suppose that, say, I want to define which is this time interval, let me call T star, okay? So the time interval that is needed for the current from V over R, which is the nominal phase current to reach 0. Okay, so in order to compute this time interval, which is the first step in evaluating the total energy, let me just discuss two results, okay, that will be just employed here. So consider a generic exponential variation of a variable x versus time. So suppose that this variable is something like this, it's an exponential variation. So I have 2 points. This point is called A, this is the B point, to which correspond the value xa, xb, and this is the time instant ta and tb. Okay, so a descending decreasing exponential function. This is the x function. The interval tb minus ta, so this time interval here, can be derived by using the standard exponential description of this curve in this way. Tau, which is the time constant, which is related to this exponential function, natural logarithm of this ratio. xa minus x at time t infinite, xb minus x infinite. Okay? Just to complete this discussion, and also because we will employ another, say, derivation later, see what happens when you have an exponential function again here, but is a increasing exponential function, like this way. Again, we have 2 points, C and say D. So we have a time Tc and a time Tt. Then we have Xc, Xd here. Again, Td minus Tc is tau natural logarithm of x infinite minus xc, x infinite minus xt. Okay, so taking into account these two expressions, in the case I want to discuss here, I'm just looking at this part here, which is a descending exponential function. Okay, so I'm using this equation here. Okay, so I have IAT, so the phase current, and I have this situation. The current here is V over RA, supposing that this is the time interval 0, and this is T star. At T star, the current is null, and then we have also the expression for the current at T equal to infinite, which is V minus BV dSS over RA, a negative value. Okay, this is IA infinite. So looking at this expression, we can say that T star is tau natural logarithm of the previous defined ratio, which is xa, so the point which is higher. So in that case, it means V over RA minus the current IA at infinite, which is V minus BV dSS over RA, divided by the current at the second point here, so 0, minus V minus BV dSS over RA. So some simple manipulation. We have, for example, array as a common denominator. So we have v minus v plus bv dss. And so we have, let me put dv ss minus v. So this is tau, natural logarithm of bv dss over bv dss minus v. So tau star, so this time interval I'm interested in is tau natural logarithm of, let me write in this way, which is the same, v over bv dss minus v. Okay, tau, of course, is LA over RA. So this is the, let's say, the time interval that is required for the current to, say, from the V over R current to reaches 0, okay, which is the point at which the MOSFET is fully open, is an open circuit. I said before that the breakdown voltage BVDSS should be, of course, larger than V, okay, in order to make the circuit to be correctly operated, okay. For example, when your voltage V is 100 volt, let me just suppose, say, random numbers here, you have to choose a MOSFET which has a breakdown voltage higher than 100 volt, for example, 150 volt, okay? Just to be sure that the MOSFET is, let's say, continue to operate correctly. Nominal operation point never exceed the breakdown voltage. So suppose just for an instant that I choose BV DSS much larger than V. Okay, if I have this, say, hypothesis, what happens that V over BV DSS minus V is very small, okay, is, let's say, going to 0. So we have a terms here, which is something like natural logarithm of 1 plus x, in which x is going to 0. So we have something that can be approximated, and the approximation is, let's say, x. So the same happens now for T star. So T star is nearly equal to tau natural logarithm of the x term, which is v, over bv dss minus v. This is if bv dss is much larger than v. Okay, so T star, tau is, of course, there is no more the logarithm here, okay? I just approximate it in this way. Tau is RA over RA, V over BV dSS minus V. Remember that V over RA is the current flowing in the phase. Let me call this current IA, capital letter, okay? Nominal current flowing to the phase when the MOSFET is on, when the phase is energized, divided BV dSS minus V. Now, this is my, say, approximation for the time interval T star, okay, the time that is required for the MOSFET to become an open switch. So let me just draw here again the current through the phase and plot also the voltage VDS. just focus our attention in the turn-off phase. So the time interval is from 0 to T star. Okay, I have here an exponential function, okay, that is, let's say, reducing itself from IA to 0, okay? And here you have the voltage, which is something like this. The breakdown voltage from 0 to T star. We are interested exactly in evaluating the energy which is involved here. Doing this approximation here, basically we have no more a exponential variation, okay? This hypothesis here leads to have basically a linear variation here of the current, okay? So this is what we add for that specific hypothesis, okay? So let me just have a description of the current decreasing at the turn-off, not just as an exponential as we did before, but with specifically a linear variation, okay? If T star is, say, very short, this is a acceptable, say, hypothesis that we can consider. Okay, which is the energy which is involved in this time interval? But the energy is the integral of the instantaneous power during the, let's say, let me call this interval 0 T star, okay? So this is the breakdown voltage multiplied by the integral of the current. This integral here basically is the area under this triangle, okay? So the area under this triangle is 1F, the base, which is T star, multiply the 8, which is IA. And so this is 1F. T star is given by LA, IA, one over BDSS minus V. And so finally the energy is, and here we have an approximation, of course, due to our hypothesis, which is 1F LA IA square multiplied BV DSS over BV DSS minus V. So as you can see, the energy which is involved in the turn-off, okay, so the energy involved in the specific region at which I'm operating the MOSFET or the switch, generally speaking, in the breakdown region is given by the product of the energy which is stored into the, let's say, inductance in the phase you are driving, multiplied by this term, okay? And this term, basically, if BVDSS minus V is, let's say, very large, this is our hypothesis, this term here is very small, is, let's say, going to 1, you can say. So, and when this term goes to 1, this is the minimum possible energy which is involved in this situation, okay? You cannot get energy lower than the energy which is stored in the inductance LA and stored in the magnetic field inductance in the previous on phase you can have here, okay? No less that this energy should be involved, okay? And this happens when the voltage, you choose a breakdown voltage for the MOSFET, which is very large with respect to B. So if you want to pray, summarizing, if you want to use the circuits to drive your unipolar stepper permanent magnet motors, there is no problem. Pay attention that you are operating the MOSFET in the breakdown region, and then you have to say take into account some specific MOSFET that have avalanche capability, and you have to look to the energy. And by the way, the minimum energy that you can have is reached when you choose for a MOSFET which has a breakdown voltage which is much larger than V, which is the supply voltage. Okay, and this can be, let's say, compliant with the requirements of the data sheet of the manufacturers. There is a drawback, of course. Drawback is that you can basically operate your MOSFET. You have to choose a MOSFET with a very large breakdown voltage. What happens when you choose for a MOSFET having a very large breakdown voltage? That the around resistance that you can have when the MOSFET is on, the resistance that you can put between the drain and the source, modeling the behavior of a closed switch, is increasing. So you have a trade-off between the energy which is involved, so the power which is dissipated during turn off, and the power which is dissipated during turn on, which is the conducting losses. Okay, because very large breakdown voltage increasing means that the around resistance is also increasing. Okay, so this is the basic trade-off you have to consider. Okay. Basically, this is not the only way you can use the circuit. Okay, you can modify a little bit the circuits. So if you want, this is an alternative circuit. Always, say, is under the L over R constant voltage driver that avoids reaching the breakdown voltage of the MOSFET. Okay, how you can do that? Let me just have the same circuit as before, so in which you have the LA, RA modeling of the phase. Then I put here a MOSFET, but you can have also the IGBT. That say discussion is the same. You have IA, the current here. The MOSFET is employed as a switch, but then I put here a diode, D. Okay, so the alternative circuit is basically the same as before, with adding this diode, which is called the free wheeling diode. Let me just see what happens at the turn on. At the turn on, the MOSFET is commanded to be on, so the voltage applied between the gate and the source, the common port of the MOSFET, is higher than the specific threshold of the MOSFET, so it's conducting the current. And so when the MOSFET conducting the current, it happens that, let's say, this node here, the drain, basically is short-circuited to the 0 volts, the reference node. Okay, while this node here is at the supply voltage V+, so the diode is off. Okay, so during the turn on, D is off. So the circuit that you can have at the turn on is exactly the same circuits we previously analyzed. Okay, so the circuits without the diode. So what we can say about the circuits, okay, that we have the same usual behavior of the current flowing through the phase. So you have always the same exponential rising current like this, reaching the V over RA, or as we called before, IA capital letter in a few time constant, okay, and the speed of this transition is dictated by the ratio V over LA. So we have, say, some specific constraints in increasing V. We cannot get faster response because increasing V means increasing IA, and this is not possible over certain specified limits. Okay, so during to now, nothing changes. The situation changes during turn-off. Because during turn-off, now what happens that the switch is commanded to be off. Okay, so the switch basically is, say, is opening. So I'm interrupting the current IA flowing in the phase. Okay, so imagine this switch here, the switch to, say, suddenly, say, commanded to be off, the current IA is commanded to, say, to go to zero. As I said before, this is not possible because there is a magnetic energy stored into the inductance LA of the phase we are driving. Okay, remember the energy 1F LA IA square. This energy cannot be vanish out suddenly. Okay, the current continues to flow, but now this current find a path which is no more the body diode of the MOSFET because the current IA flow in this path here. This path does not involving the MOSFET. Okay, the MOSFET has a current ID which goes to zero, say, in a very fast way. The current continues to circulate in these specific small circuits composed by LA, array, and a diode. Which is the circuit that now we have to consider for understanding the time evolution of the current in the phase. The circuit is basically this one. When the diode is on, we can replace the diode by a small battery voltage. Let me call this VF or V gamma, which is the on voltage of the diode conducting. Okay, so the current here is IA over T here, and this is the circuit. We want to define the time evolution, but the circuit is always the same circuit we previously analyzed. There is no surprise. Okay, so we have the same evolution, IT, which is I infinite minus I infinite minus I0 plus E minus T over tau. Tau is all A over RA as usual. I infinite is the current flow in these circuits at, say, when all the transients are vanishing out, and this is minus VF over RA. Okay, when all the transients vanish out, the current flows exactly in this direction. Okay, exiting in this way, and then I0 plus is the same of I0 minus, which is V over RA. So what happens that if you look at the evolution of the current, you can see something like this. Let me include also the turn on, which was previously analyzed. Then I have here the turn off instant. I have something like this. I don't know which is the level, but the infinite level is minus VF over array. And this is IA. Okay. So basically the same time evolution that we have before. Of course, this section here is not physical quantities, because when the current IA goes to 0, the diode becomes off. So the diode is interdicted and it opens up. Okay, so here the diode will become off. And if the diode becomes off, that the IA current is 0 and continues to be 0. Okay, so the physical part is just having positive current. Okay, and it's not possible to have current flowing in the direction this one, of course. Diode would become on. Anyway, there is a time interval even here. That is the time interval I have to wait before the phase current goes to 0. Okay, which is again from say, let me call this T 2 stars. Can we analyze this time interval? For sure, because we know that there is a specific relationship for exponential variation. Okay, let me just use the same formula I employed before. So tau, natural logarithm of what? You have to consider which is the current here, which is IA, so V over RA, minus the infinite current, and so we have minus VF over RA, divided by the current that you can have in the second point you are interested in. So here the current is 0, minus VF over RA. This is tau, natural logarithm of V plus VF over VF. And so it's tau, natural logarithm of 1 plus V over VF. Okay, this is what happens in that specific situation when you have the freewheeling diodes. Just compare this expression here with the expression for the time star interval we got for the previous circuit. Okay, this is something like 1 plus this one. Is basically is the same, say, shape, tau, natural logarithm, 1 plus V, and then we have another denominator. So let me put in the same slide and the same page to compare them. T star is tau, natural logarithm of 1 plus V. And so the only difference is that you can have BVDSS minus V here. So if you compare this quantity, you have here VF, and then we have BVDSS minus V. So VF and then BVDSS minus V. VF is the on or the forward voltage drop of the diode D. Okay, while this is the difference between the breakdown voltage, which is specified for the MOSFET you are choosing, and the supply voltage. Okay, and this quantity here can be any value which is enough larger, okay, to say have safe operation. As I said before, in a say example, if V is 100 volt, the breakdown voltage can be 150, just to be sure to not match this characteristic. Or if you want to minimize the energy, okay, if you want to reduce the energy involved in the breakdown region, BVDSS is much larger than V. So this leads to the consequence that the voltage VF, which is, let's say, 1 volt, 1.5 volt typically is always less than this difference BVDSS minus V. And so this has a consequence, because T star, double star, is typically larger than T star. Okay, so we add a freewheeling diode, and we solve the problem of having a MOSFET, or as a switch, operating into its breakdown region. That is always something which is not very safe, let me say. But anyway, we have the problem of having a turn-off time which is larger than you can have before. So let me just sketch the behavior of what happens here. This is the current, which is V over RA during the energization of the phase. Then you have the de-energization of the phase, you have the turn-off. What happens about the voltage VDS? The voltage VDS is something which is very close to zero when the MOSFET is on. And then what happens when you are turning off your MOSFET? You are not going no more in the breakdown region. You just have, let's say, here something which is V plus VF, because here the diode is conducting, then you can go in V. So the MOSFET here is on, MOS on, D off. Here the D is on. Here the D is off. But in both situations, the MOSFET is off. Okay? What happens to the current flowing through the MOSFET? The current flowing to the MOSFET, let me put in the same graph you can have here, ID T. Now the current flowing to the MOSFET is no more the same current flowing to the phase. Basically, is the same current flowing to the phase when the MOSFET is on. But when the MOSFET is off, it goes, say, basically in a very fast way to zero. Okay. Anyway, this time interval, T double star, for the red curve, okay, is larger than T star. So we solved the problem here, because now the MOSFET has, say, a voltage which is no more large as the breakdown voltage. Basically, the current is almost null instantaneously. So the power dissipated is basically, say, very close to zero. There is no such kind of high energy dissipated as in the previous situation, but the turn-off, say, lasting a little bit more than the solution without the freewheeling diodes. Okay, so what does it mean? That this solution implies that if you are increasing the frequency, then your torque for very large pulse per second is reduced, because you have, say, a very large turn-on and turn-off phase. So you can say that for if we want to put the torque versus the pulse per second, this is a graph that we already seen. You can get something which is very, say, here. Okay, so you can get the maximum torque just for very small values of the pulse per second, the frequency. Okay, then very, very fast way the torque is decreasing, because this is not compatible with this large time interval at the turn on and at the turn off. This happens for the L over R driver. Basically, remember that we saw a graph of this torque versus pulse per second in the slides provided by a manufacturer, which exactly states this behavior here. Okay, which is very poor torque behavior versus frequency due to exactly this very large turn on and turn off time interval. Have you questioned about this description, something which is not so clear, something that you think requires explanations? Of course, you have to solve this problem just to make it possible to increase the operating frequency. We can start solving problems. For example, looking what happens at the turn-on. Okay, the turn-on for both the circuits we analyzed so far, they react in the same way. Okay, they have the same turn-on behavior. As this turn-on behavior cannot be accelerated because you have that V is something that you cannot increase too much. Okay, the slope depends on V, depends on also on LA, but LA is something that you cannot modify. Okay, depends on the motor we are choosing. And so the motor typically is the side basically looking at the torque capability. Okay, it's not just giving, say, indication about the inductance. So you have some free parameter, which is the voltage V. If you want to increase the speed of the turn-on, you have to increase V. But if you increase V, also you are increasing the current here. And then the current here is not free to move with very large values. So let me just introduce the R over L driver. Okay, up to now we discussed the L over R. The R over L, sometimes they are called constant current driver. In this kind of situation, this kind of circuits, we exactly increase the voltage V in order to speed up the turn-on. Okay, but to solve the problem of the current. Okay, let me just consider this circuit, which is basically the same circuit we are used to consider so far, which is LA, RA. This is our phase. Okay, this is the model of the phase. These parameters are defined in the datasheet. Okay, they are not discrete parameters that you can add into your circuit. But then let me put here another resistance. Let me call this R, let's say V, which is a discrete resistors that I can put in the circuits in series with the phase. And then we have the switch, for example, a N-channel MOSFET. So I add this resistance, okay? Just consider the circuits because at the turn-on, both the previous circuits with or without the freewheeling diode are the same. Okay, so here you can have also the freewheeling diodes across the phase, and the circuit is working as usual. But at the turn-on, the diode is off, and so there is no difference. The current flowing here, when the MOSFET is commanded to be on, so at the turn-on, basically will become IA, so the nominal value, and this nominal value will be V divided by RA plus RV. Okay, now we have this, say, term here that before was not present. Okay, now suppose that I want to maintain this current at a safe level, the maximum possible level that manufacturer specified in the datasheet. Okay, so this is for these circuits, let's say R over R. And let me put this current equal to the same current that you can have in the circuits that is the R over R driver. Okay, of course, in order to have the same current, the voltage V that you can have here is not the same voltage V you have in the L over R driver. Is something that we can call V prime, okay, in which V prime is larger than V. Okay, since the current should be the same, you can see that V prime is something like V multiplied 1 plus RV over RA. So V prime is larger than V by this factor here. Typically in, say, practical circuits, RV is, let's say, from 2 to 10 times RA. Okay, so the voltage here, V prime, is something like, I don't know, 3 to 11 times V. Okay, so we are employing a solution by putting this resistor in series that makes possible to get the same on current, the same current flowing to the phase when the MOSFET is on, so the phase current, increasing the voltage V, which a minimum, say, 3 times the value you get without this resistance to up to 10 or more values. Okay, so what does it mean in terms of, let's say, turn on rapidity? That my turn on is effectively increased. The current is always the same, is IA. But now we have something which is more faster than before, because now the slope you can have here is V prime over LA versus the slope you can have for the L over R, which is V over LA. Okay, so basically 3 to, say, 2, 3 to 10 larger value. Okay, this is for L over R driver, and the red one is for R over R driver. Okay, so we have a means to speed up our circuit. Then at the turn off, what happens? At turn off, you have the, say, let me put here the freewheeling diodes, okay, which is, say, in our circuits, the MOSFET will become off, the current recirculate in this circuit here, okay, making the diode to be on, and now the time constant is something like RA over RA plus RV. So basically, what happens here is that even the turn off can take advantage of this resistance, okay, if you put your diode connected here, because the time constant is, say, reducing, okay, and so even the turn off will be a little bit faster than T double star I have before. Okay, so basically this solution leads to a say, behavior of the torque versus the frequency of the input pulses, which is a little bit better than before. Okay, this is the L over R, and you see the R over L can be something like this. Okay, for example, you can take the same torque, okay, for example, this torque here at pulse per second that can be larger as, let's say, 10 times the pulse per second you can have for L over R driver. Okay, so this is the major benefit in having these circuits. Of course, no benefit comes without any drawback, and the drawback here is easily understood. That is the power which is dissipated by this resistor. Okay, so the current flowing to this phase is the same as before, but now the resistance is, let's say, 10 times that you can have in the L over R driver. So even the power which is dissipated in the winding is larger than before. So in terms of heating, the winding here are a little bit warmer than before. Okay, they are, say, specifically, they can be, let's say, even larger in the section if you want to consider this behavior. But anyway, this can be a possible solution. Okay, of course, this is not the end of the discussion, because we can do much better than we saw up to now so far. Okay, for example, just summarize all our understanding up to now, and then we prepare something that I can explain tomorrow. Okay, for example, let's start from the turn on. Okay, I can increase the turn. I can say increase the time constant of the turn on by adding this resistor. Okay, as we did here. But basically, this is something that can increase a little bit the torque, which is the main, say, limit of this kind of analysis, of this kind of behavior. The limit is that I have always to wait for the current reaches the nominal IA current. Okay, my transient here, the time interval at the turn on delays, is dictated by the fact that I have to wait the current going from 0 to IA. So I have to wait for the transient to be end. But what about the fact that, for example, if I increase the voltage V to very large value, but I know that this has a very huge impact on the current flowing IA in the phase, okay? But why I have to wait for this current to go exactly to the current IA? Why I cannot, for example, suppose this fact. This is the current IA, and this is this time. Suppose that I choose for a very large voltage. A very large voltage V is applying the circuits in order to have the fastest response at the turn on I can imagine. Okay, of course, if I use this voltage here, my current will be very huge. Okay, because this is V over RA. RA is fixed by my motor, and V is the large voltage I am employing. And for example, this voltage is several times larger than the maximum possible voltage that manufacturer established in the datasheet. Okay, so there's no way. But if I add something in the circuits, let's say a control circuit, that in the exact instant in which the current IA overcomes the maximum possible current here, for example, stops the switch, so open the switch, or make some action in order to maintain this the current to be constant, having a large voltage is no more a problem, because I have not to wait for the complete transition of the current following the, let's say, exponential behavior. Okay, if I have something that recognizes that I reached the maximum possible current provided by the datasheet of the stepper motor I'm using, and then say maintains this current to be constant, that I can always employ a voltage V larger as I want. Okay, so first of all, I want to say employed a different strategy for the turn on. Okay, not waiting for the transient to be end, but just maybe including something more that say understand which is the maximum current that I have to phase off. But this is say separate, okay, the choosing for the voltage with the current level. Okay, I have to decouple these two parameters, the voltage V and the nominal current, and this can be a good choice. The second problem is that I have to accelerate also the turn off. I have some indication about what I have to do according to my previous discussion. Okay, Let me just to go back to the L over R driver without any breakdown voltage, without any, diode, freewheeling diode. I said that here the T-start time interval, which is the turn on, is shorter than that T double stars you can have when you use the freewheeling diode. Okay? Why this is shorter? Why this T-star is short? Because I said before, this depends on this, let's say, where it is. Depends on this difference here. When you are at the turn off, the phase of your stepper motor is subjected to a voltage which is negative voltage, which is VF, the small voltage drop of the on diode. Okay, see here the voltage, let me call this VA, the voltage across the phase, basically is the voltage minus VF. Okay, you can see here in a very precise way. VA is minus VF. While when you do not have any freewheeling diode, the voltage across the phase at the turn off is, and this maybe is embedded in some page here. Here, the voltage across the phase here, VA, is V minus BV DSS. Okay, it's exactly this comparison we made before. VF is less than this voltage here, which is negative. Okay. This is totally understandable or reasonable, because when you have an inductance, the voltage across the inductance is L the I on the T. And the I on the T, and I is the current flowing, and V is the voltage across this inductance, then it is the slope of the current versus time depends on the ratio between VL and the inductance itself. So it depends on the voltage V. If you want the I on the T negative, it means that you need VL, which is negative. And higher is the negative voltage applied to the inductor, higher will be the, say, negative rate of the current versus time. So if you want to have the turn off time very small, you need a very large negative voltage applied to the inductor. And this is exactly what happens in our previous discussion. T star is, let's say, smaller than T double star because in the situation which you do not have the freewheeling diodes, the negative voltage applied to the inductor at the turn off is V minus BVDSS, which is negative and very large with respect to the negative voltage applied to the inductor when you have the freewheeling diode, which is the small minus VF voltage drop across the diodes. Okay, this is the reason basically why when you have the freewheeling diodes, okay, you have a larger turn-off time. So according to this discussion, which is now is totally clear, if you want to increase, if you want to increase the speed, so you want to decrease the turn-off time, you have to apply during the turn-off phase the largest possible negative value across the phase of the motor. Okay, so two basically techniques are needed to, say, make faster operation of the stepper motor, increasing, for example, the torque to, let's say, behavior like this one. Okay, and is to avoid to waiting for the current to reach, let's say, the stationary situation, possibly including a system that when the current reaches the maximum possible value, then it, say, do something to maintain the current to be constant at that value without expecting all the transient, and so these decouple the voltage V that can be very large with the current IA, and at the turn off applying the highest possible value of the voltage negative across the inductor to speed up this turn off. Okay, these are basically the two situations that I want to exploit for another circuits, which is called the chopper drive for stepper motor. Okay, that I explain tomorrow. Any questions, problems? Antonio Moles, can you repeat the technique of the turn off? Which technique? Sorry, I just see your question now. Which the technique? This technique for accelerating the turn off. This is the question. To speed up. To speed up is that basically is the technique that is described here. It's not a technique. It's a philosophy, if you want. Maybe basically the phase of any motors, but in this case the stepper motors, can be described in terms of inductance in series with the resistance. Okay, do not neglect the series resistance just for now, just for a moment. Okay, if you have just the phase which is described by the inductance, you can see that the characteristic expression that link the voltage and the current in the inductance is this one. Okay, in which the I on the T, it represents the slope of increasing or decreasing current through the inductance. Okay, in this case, the current through the inductance is the phase current. I'm just looking at how fast can I decrease the current flow into the inductance. So I want to have the I on the T negative and very large. In which way you can have the I on the T negative and very large, according to this description, is needed to have voltage VL across the inductance, which is very large and negative. And this is what I want to exploit. When I want to turn off my phase, I have to apply a very large negative voltage across the phase. And this is in totally accordance to what we saw in the previous discussion. In fact, when you have the L over R driver without any diode, at the turn off, the voltage across the inductance, across the phase, is negative and quite large because it's V minus BVDSS, in which BVDSS is larger than V, or much larger than V. When you have the freewheeling diode in the same L over R circuits, the voltage across the inductance is negative, but it is not so large because it's just the minus VF, which is minus 1 volt, minus 1.5 volt. And this leads to the fact that T double star, so the turn off time for the circuits which you have the diodes, is, let's say, larger than T star, which is the turn off time for the circuits which you don't have any freewheeling diode. Okay, so the technique, if you want to call it this way, is just to accelerate the turn off by applying the larger negative voltage across the phase. Okay, something that we will exploit tomorrow morning, starting 11:30. Any other question? Problems, issues? Okay, guys, if you have no questions, the lecture can be stopped here. See you tomorrow morning.